Hello, my learners. We are going to talk today about these non-homogeneous second-order linear equations, or the non-homogeneous or some non-homogeneous equations for second-order linear operators. We've been talking about, let's see if we can move this. We've been talking about equations of this form right here. This is the homogeneous equation for this second-order linear operator. But now what if we stick it equal to something other than 0? How do we find solutions for that? Like this might be x e to the x or sine of whatever x, who knows what. We're going to find out later with physical systems that if this is representing different forces in play, that this thing right here will be some outside force acting on the system. Okay, so it's physically important to know how to solve these. And this is like the simplest case of these. Okay, so how do we go about doing that? Well, it's nice. We've got this theorem that's going to help us a lot. Let me go to the next page here. And let's line ourselves up a bit. Okay. And what we've got here is that if you have a non-homogeneous differential equation, like we saw with the g of x, then any solution can be written as the solution, the general solution for the homogeneous equation. That's the y sub c they're calling here for the complementary equation. And just one specific particular solution. All right, so really it's saying that all the play that can occur in the different solutions you can get for the second order differential equations occur in the part of the equation that just gives you 0 out of the linear operator. And that if we add on to it anything that can give us that g of x on the other side, we will have a representation of all possible solutions. And they give a proof, and the proof is because you apply that linear operator across here. The linear operator hits this, and plus the linear operator hits this. The linear operator hits this, and it gives me 0, because this is a solution to the linear operator of y equals 0. And then this gives us that g of x that we saw a second ago back here. Oops. Here. So the y sub p stuck into here will give us g of x. The y sub c stuck into here gives us 0, and then g of x plus 0 is g of x, and that's how that game is working. Okay. Now what I want to do is, instead of going into the theory about all of this, I'm going to start with the example they use and then use Mathematica to kind of walk through the example. So they're trying to solve, okay, select that, this operator. So what we first do is to find the homogeneous version, or what they call the solution to the complementary equation. Okay, so it's y double prime plus y minus 2y equals x squared. So I'll bring up Mathematica. Where are you, Mathematica? Mathematica, where are you? I don't see it. Ah, there you are. Okay, excellent. And I'm going to raise my screen up just a hair. Perfect. Okay, so what did we have? We had y double prime of t plus 2, or was it plus y prime of t minus 2 equals x. Oops, sorry. In this case, it would be t squared. And it's equals there. All right. Let's make sure that's what we had. Minus 2y. Duh. I know that. Minus 2y. Otherwise, it wouldn't be a linear operator now, would it? There we go. All right. So the first thing we do is we solve the complementary one. So the first thing we do is solve the complementary. Which is what? It's the same equation with a 0 there. Now how do we do that? Well, we get the roots of the characteristic equation, or what they call the auxiliary equation, which is what? So the auxiliary, I think that's how you spell it, equation is what? It's r squared plus r, crazy, r minus 2. And we'll solve this. All right, so we get 2 real roots. That's good. We know exactly what the complementary solution will look like, the homogeneous solution will look like. And what is that? It will look like, so we can call this yc of t, and we're going to define it to be what? C1 exponential of minus 2t plus C2 exponential minus t. Okay, now we're going to check it. How do we check it? Well, we take this equation right here and copy it, pull it down, and I'll put a C in there so that it will actually do it. And then I will go ahead and remove that. Oops. Gave me that. And let's expand. Ooh, I did something wrong. What did I do wrong? Ah, right here. That's positive 1. Ah, excellent. So this is the complementary solution. This is the solution to the homogeneous version of this. Now, the next comes this method of indeterminate coefficients. And basically, it's us guessing what a particular solution, because we only need one. And the obvious guess, if you had no other choice, is to guess that a quadratic polynomial. So now we're going to be, so let's write this. We now hunt for a particular solution. So you guess it. And this is how I would do that. I would go yp, let's just define a function, okay? So that way when we stick it in, everything is going to work, and then we don't know what the coefficients for this function should be. Alright, so that's what we're going to, oh, capital C is a bad idea. We'll use little c, and as a matter of fact, we'll use little letters on this because of that. Okay, so that's what we're going to guess our function looks like, but we're on a hunt to figure out what a, b, and c need to be. So what we do is we just go ahead and stick this equation in down here, come down here, and we put a P, 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 and we hit enter. Now what we want to do is just go ahead and expand all this out, see if it will simplify it, do something for us. So okay, so everything on this side has to be equal to everything on this side, term by term. So actually, I think what I'm going to do is do this command, collect on t. And what that does is it goes through and says, okay, everywhere I see, and actually I think I can collect on powers of t by putting a little line there. That's an underscore. Let's see if that works. Nope, that didn't work. Let's see. Yep, that worked. All right. So what that is saying is collect on powers of t of different values up here. There ought to be some type of something else I could write up there, but I think that's it. Now, what does that mean? This means that I need several things to be true, and we will write those in a solve. I need 2a plus b minus 2c. Those are all the things that are our constants over here have to be equal to the constant over here. Well, what is the constant over here? It's 0. And I need this thing to be equal to 2a minus 2b. What do I need that to be equal to? Well, what is the coefficient of t over on this side? 0. And I need minus 2a to be equal to the coefficient of t squared over on this side, which is what? 1. And those are all the things that have to be true to find the correct coefficients. So I put those and I say, all right, please solve for a, comma b, comma c. Let's see what it gives me. Aha! It says there is a solution. There is something of this form right here, as long as a is minus a half, b is minus a half, and c is minus 3/4. So a way of checking that is just taking this right here, put it up here, right there, and we can actually just take a peek of what that yp of t is going to look like before we compute. So let's do that. Boom. So y of p is minus 3/4 minus t over 2 minus t squared over 2. And when we put it into this, we get this, but the minute we expand it, it's true. And then, of course, if you try to collect terms, it means nothing. Excellent. Excellent. So we've got our yp. We didn't remove that. We should do that. There. The blue tells me it's removed. I've got the solution that can make this equal to 0, and I've got a particular solution that makes this thing equal to t squared. So if I add them together, because this is a linear operator on y, if I add them together, I get a solution that gives me this plus 0, which is just this. So my general solution is going to be what? Well, it's this. Actually, I'll just copy this whole thing because I'm going to use it. Our general solution is what? Y of t and plop that down. Take this out. So it's that, which is the homogeneous solution or the complementary solution, plus, I'll just grab that, plop it down, and that's my general solution. Now let's check it out. So I'll grab, let's say, this. So I'll take the p's out, because I'm just going to check this as a solution for y. What do I get? Oh, that can't be right, right? Wait a minute. Let's tell it to juggle it around, jiggle it up a little bit, see what happens. True. So the solution we would get is any real number times exponential minus 2t, any real number exponential 1t, minus this polynomial. Now let's see what the book says. Alright, let's see if we can grab this. Well, they came up with our complementary solution, and they wrote out what they think the particular solution is going to be. And then let me move this over. Then look what they did. They did basically algebra to figure out what those coefficients would be. And after doing that, lo and behold, they get our solution. See how it works? Let's try another. Let's try this one right here. Y double prime plus 4y equals e to the 3x. This time I'll be smart and I'm going to use x instead of t. Okay? So let's come back. And actually, we will scroll. I can actually just move this screen. I'll scroll to the top and say example 1. And now we're going to do example 2. And let's walk through it. Let me just remind myself again what it is. Y double prime plus 4y equals e to the 3x. So what do we have? We have y double prime plus 4y. We should put t's in there. Oh, not t's. Alright, Mr. Book. Let's see if we got that right. Yes, we did. Well, excellent. Okay, what's the first step? First step. First step. Solve complementary equation. Which is what? The homogeneous equation for that linear operator on the left. As a matter of fact, we'll just call that YC. I notice that Y hasn't been removed because we actually named it, didn't remove it back up there. So we have to be careful of that. Okay, so we've got YC, right? Matter of fact, we probably just won't remove anything. Ugh. Okay, what do? Well, we solve the complementary. We solve the characteristic or the auxiliary equation. So solve what? Solve what? Solve. I think we can see this one coming. Minus 0 minus 2i and 0 plus 2i. So remember, you need to know what the real part is. So what does our solution look like? Our solution looks like yc of x, c1, exp 0x cosine of 2x plus c2 exp 0x sine 2x. Okay, because we use the absolute value of the imaginary part for this part in here. It all works out. Okay, now of course this could be simplified. this doesn't exist at all. So it's just c1 cosine 2x plus c2 sine 2x. But I'm just putting this in here to remind you that this is actually the two full real part, imaginary part, real part, imaginary part. That's how it works. Okay? And we know it's going to work, but let's check it. So we'll come up here, grab this. First we'll go yc of x, just so we can get a picture of what it looks like. We pop that in, see what that does. Aha, c1 cosine 2x, da da da. And we expand that out. And looky looky. So that is a solution. So next step. Well, now we have the part that gives us all the different possibilities. That comes with the homogeneous solution part. Now we just need to find one thing that makes this true. Now what do you think that would look like? Think about it. Well, your first guess might be, well, how about just something times e to the 3x? And that's a pretty good guess, so let's try that. So next step, figure out a particular solution. Just one solution, and maybe even spell particular correct. It never does what I want on that. Yeah. Particular. There we go. Nice. All right. Well, let's guess the following. Let's guess yp of x equals what? A exp 3x. Okay? And let's stick that into the equation and see what we get. We'll just put a p in here. See what we get. So what does that mean? Let's see. We need, it already kind of simplified this down, so what we need is 13a e to the 3x is equal to e to the 3x. So the coefficients for like terms, and you can actually just divide these terms out, but the coefficients for like terms have to be equal, so what we need, it's kind of silly to even write this, but we can. What we need is just one thing to be true. Right? And we can check it. So we can see that, and we'll take this out. We'll slash dot that. Sure enough, it holds true now. Okay, so now we have our full solution. Let's check it out. We've got y, x, a complementary solution, yc, plus our particular solution, yp. We'll take a look at what that's going to look like. Just get it to print out what it's going to look like right there. And we'll check to see if it actually solves this equation. Certainly doesn't look like it, but there's so we'll cover that mess up and see what it looks like expanded. Ah, and it's true. So it does solve the equation, and it represents all possible solutions to this equation, where this zeroes out. Now what's going to happen here? I mean, one of the things you could ask yourself is, okay, what does this solution look like? Well, this solution here is just oscillating back and forth over x. And this solution here is blowing up. So you could do something like plot. Let's see what this looks like. Plot e to the 3x. All right, we can see what that looks like. You could plot, and let's just make that a 1. You could plot this. You could plot one example of this, which maybe let's say is, we'll make that a 2 and that a 1, maybe, or a -1. And then you could try what a general solution to this thing looks like. Or we throw this in. Let's see what all these look like and see if we can spot them as they come out. So x can go from, let's say, -3 to 3. All right, so this curve right here is the e to the 3x. That's what exponential growth looks like, right? Let's see, this green and this, this yellowish green and this purplish color are two oscillating ones. The green one is this solution, and notice that this blue one, which is the combination of the two solutions, is the full solution that solves the whole equation. When you go back in time, go back in x, this term becomes negligible, and you're just doing the same thing as this green curve. But as you move forward in time, this is what becomes negligible compared to this, because you're going to get a very large number plus some bounded thing. So it pretty soon is going to look just like this purple. Okay? Well, let's do one more, do something a little more complicated. Close this down. Do one more. Let's see what we can get ourselves trouble into doing sine x. Maybe we can do something a little more complicated than that. That looks pretty complicated. So let's do that one. Y double prime minus 4y equals x e to the x plus cosine 2x. Let's try that. Okay. So first of all, y double prime minus 4y. What was that, example 4? Okay. So what do we have? Y double prime x. Are they always stuck with x? Lord, yes. All right. No problems. No problems. Minus 4 y of x equals x. We'll get fancy here. E to the, what was it? 1x cosine 2x. X plus cosine 2x. All right, so that's what we're trying to tackle. Step 1, we want to tackle the complementary equation, right? So we pull this down, we put some p's on it. Oh, actually, yeah, put some p's on it, and we're trying to solve that. So what are we doing? Well, we are writing down we're actually going to solve the complementary equation for that. Not complementary, the auxiliary equation or the characteristic equation for that. So that's what r squared minus 4 equals 0 minus 2 and 2. Good. Two different real numbers. We know how to deal with that. So we're going to have what? We're going to have for yp, we'll redefine it to be C1 escape minus 2x plus C2 2x. We'll look at what that looks like, and then we'll stick it into this equation and just to check that it's true. See what that looks like. Ooh. Well, maybe if we expand that equation out, we can get the all go sign. Excellent. All right, so we have the complementary solution, the solution to the homogeneous version where this is all 0. Now all we have to do is just hunt down one solution that works where it ends up over here being this, x e to the x cosine 2x. How do we do that? Well, we have to guess a possible solution to this. Now Mathematica may not, in the book it may break those guesses up into parts because we got a sum here, so you can kind of figure out what this needs to be, what the part of the solution will give me this, and another part of the solution will give me this. And there you're using the linearity of this operator, that you can deal with each part individually. But because we have Mathematica, we can just deal with all these parts at once. So we can guess a solution. We'll pull this down. And we're hunting for a particular solution. Come to the top of the screen, pop that in, put a P in there. Now what are we going to guess? Well, we're going to guess, let's walk it through. Okay. Well, we've got a polynomial of 1 degree times e to the x. So we're going to guess a first degree polynomial times e to the x. There's no reason to believe that having a higher degree is going to work out because we'll pick up that higher degree in this term here. So ax plus b x. And now what about this? Well, sines and cosines all rotate around to give me sines and cosines. So something times a cosine 2x and a something times a sine 2x. So we'll use c cosine 2x plus d sine 2x. Okay, so that's what we're going to guess. We will make sure that we're getting what we bargained for. We'll just print that out, and then we'll grab this thing, and it will tell us what this put into here looks like. So let's just run that. Okay. So now what we need is all the terms on this side to match all the terms on this side. So I think what I'm going to do is do a collection. So I'm going to say, all right, collect on that last one. What do I want to collect on? I want to collect on e to the x. Well, yep, that's all the terms I can get. I got a e to the x term. I got a x e to the x term. Put a space in there. I've got a cosine of 2x, and I got a sine of 2x. Okie dokie. So what do I get? Over here it didn't quite do what I wanted it to do. I wanted it to collect on x, e to the x, and on e to the x, but I guess these two are too close together for it to collect on that. So that's okay. That's okay. That's okay. So one of the things I see is that I need this to be equal to what? Well, actually, I take that back. It's just not that clear at all. Oh, no, it is. Yes, it is. Yes, it is. I need this to be equal to x. I need this to be equal to 1. And I need this to be equal to 0. Okay? And this breaks up into two parts actually. I need, because that's a 1 sitting there. So I actually need 2a minus 3b to be equal to, let's see, 0. So I'll write that in. I need 2a minus 3b 0. And I need minus 3a to be 1. So here are the things I want to solve. I want to solve. I want that to hold. I'll pull this down. I want that to hold. And I'll come over here. And I want that to hold. And I'll come over here and I want that to hold. And I want you to solve that for A, comma B, comma C, comma D. Go. Yeah, I didn't need that. I should have erased that. All right, there we go. Lo and behold, I get my coefficients. So if I come back up here with these coefficients, and actually, instead of doing that, I think I might copy this, pull it down, give it a new line. Copy. I do that, and let's see how it works out. So there's the solution it's suggesting. That doesn't look like it's going to come out to be 0, but let's make that quiet, but take it and expand it out and see if it figures out anything. Lo and behold, it's true. All right, so I have my particular solution, and I have my why was I calling that YP? This is all C. I want C there. C there. C there. There. And so my general solution is that. And we will first check to see what that looks like, and then we will plug it into the general equation and see if it works, except we get rid of all these p's and we just do it the general equation. So we clearly need to expand that. So here's our general solution. This part of the solution gives me 0 when the linear operator hits it, and this solution here gives me that part. So every solution to this second order linear differential equation looks like that. And that's how the game goes. It's determining those coefficients, determining the homogeneous solution, get the particular solution by guessing the general form of the particular solution and then finding out what the coefficients need to be and then adding the two together. And then maybe if you're given an initial conditions, then apply the initial conditions to see what you need. Okay? Good luck with this, and I will talk to you Friday.